everyone. Welcome back to the lectures on Introduction to Maltesian Systems. While we were discussing the spectral properties associated with an adjacency matrix, we realized that certain kind of graph structures or network topology can lead to many interesting properties associated with the spectrum of the adjacency. Just to give an example, if the network topology is such that the underlying graph or the adjacency becomes rho substochastic, then we remember that certain network structures can cause every eigenvalue in the matrix to become less than 1, making the network or making the system convergent, making the distributed averaging system a convergent system. Similarly, can we say such nice properties about the Laplacian matrix as well, which is something that we will discuss in today's lecture. So let's get started. In a previous lecture, a few properties associated with the Laplacian matrix. In particular, we discussed how 0 is always an eigenvalue of every Laplacian matrix that we can have, irrespective of the nature of the graph and every other property. If it's a Laplacian matrix, then 0 is always an eigenvalue. So now, thereafter, we had posed a few more questions pertaining to the 0 eigenvalue. The first question is 0 always a simple eigenvalue of the Laplacian? Meaning, is it true that 0 occurs, is not repeated and occurs only once as an eigenvalue? The second question is, suppose we assume that the answer to the first question is no. 0 is not a simple eigenvalue and hence is repeated. Then the question becomes, if 0 is a repeated eigenvalue, then is it now semi-simple? What is a semi-simple eigenvalue? It means that the algebraic multiplicity of the eigenvalue is same as its geometric multiplicity, meaning all the Jordan blocks associated with that particular eigenvalue have a dimension of 1. The third question says, okay, let us say if it's a repeated eigenvalue, it's a semi-simple eigenvalue. But the point is, when can we say it is a simple eigenvalue? And when can we say it is a semi-simple eigenvalue? Or perhaps it is simply repeated, not being semi-simple. So the question is, what are the factors which determine such spectral properties of a Laplacian matrix? So in today's lecture, we will start by answering this question, which tells us about the graph theoretic properties under which a Laplacian has 0 as either a simple eigenvalue or a semi-simple eigenvalue. Thereafter, we'll discuss some general spectral properties associated with the Laplacian. In order to answer this question, let us first try to understand some other properties that are associated with the Laplacian. Let's get started. What we'll start by is, we'll start by constructing row stochastic matrices from a Laplacian matrix. Now the question is, why would we want to do that? Let me first write it. So, row stochastic matrices associated with the Laplacian matrix. So please take a note of a few things here. First is, we have said a Laplacian matrix, meaning we start with a diagram and focus on its Laplacian matrix, which is obviously unique. And then we try to see if we can construct a row stochastic matrix out of it. Also, we try to see if we can construct more than one row stochastic matrices out of it. So can we do that? And how can we do that in fact? So let's get started. So let's start by considering a diagram G containing and number of nodes, number of nodes, the Laplacian matrix of G is denoted as L of G, as always. So we now have a Laplacian matrix. Now, let's start with the Laplacian matrix L. You already know a few things. In fact, let us rather start with a diagram before we state the results. Let us start with the following example. We have a diagram like this. This, and let's say this. Suppose this is a diagram and the edge weights run in this manner. And one more edge from here to here in this manner. And suppose we say that, let me write the edge, let me index the nodes. Now we say that 3 is connected to 2 and 3 is also connected to 1. This is what our diagraph looks like. Now let's write up its Laplacian matrix very quickly. So the Laplacian is a 4 cross 4 matrix in this case, such that L11 is simply equal to D out, which is 1. And here we will have a -1. Similarly, in fact, let us add one more node to the network. And let's call it node number 5. This is our node 5. And suppose node number 5 has an edge from node number 3. Now let's continue writing it. Our Laplacian now will become a 5 cross 5 matrix. Okay, so what will it look like? Let's see. Okay, the second row, 2 has 1 and 2, now degree of 2. So this here is 2 and its edges go to 3 and 4. So meaning we will add -1s here because that is what. So since edge weights have not been explicitly written, we'll assume them or we'll consider them to be equal to 1. So unless otherwise specified, we always take the edge weights to be 1. Now node number 3, if we see, has 1, 2, 3 and 4. And now degree equal to 4. This is 4 and it has an edge to every other node. Node number 4 has an out degree of 0. And node number 5 also has an out degree of 0. Let me define L max as the maximum of all of the diagonal entries. In our case, that is equal to 4. The diagonal entries are 1, 2, 4, 0, 0. So obviously, the maximum is equal to 4. Let me define yet another term, which we call as epsilon. So what is this epsilon equal to? We choose epsilon to be less than 1 by L max. Meaning, for our case, let us simply choose epsilon is 1 by 5. Now, as we know here, L1n is obviously equal to 0. What about epsilon L1n? Is it equal to 0? Obviously, yes. So that can be easily verified. It follows directly that epsilon L1n is equal to 0n. Meaning the row sums of the new matrix epsilon L also add up to 0. So what are the row sums of epsilon L? Now let me write this here. They would become equal to 1 by 5. Again 1 by 5, 1 by 5, 4 by 5. And the rest of the entries remain 0. So as you can see clearly, every row sum is still equal to 0. Now let us define a matrix R. Sorry, let's define it as AR, meaning A, row stochastic, being equal to identity minus epsilon L1n. So the claim is this matrix is a row stochastic matrix. Let's quickly verify what it will look like. For the given example, AR being equal to IN minus epsilon L1n is simply equal to let's see. So all that we are doing now is, let me add 1 minus epsilon here, meaning 1n minus epsilon. So 1n is a diagonal matrix, meaning what changes here? The diagonal entries of this new matrix get changed. It is simply 1 minus this entry. Yet another interesting thing happens. What happens to all of the off-diagonal terms? Do they now become non-negative? Yes, because when we do minus of L or minus of epsilon L, all of the off-diagonal entries now have either a positive sign or continue to remain equal to 0. Hence, let's quickly write up these values. So this, for the given case, is equal to, let's see. So the first entry simply becomes equal to 4 by 5, similarly 3 by 5, 1 by 5. Let's write up these entries. This here is equal to 4 by 5. And what about the rest of the entries? This entry simply becomes equal to 1 by 5. And the rest of the entries continue to remain equal to 0. So what is the sum of the entries in the first row? Note that they now add up to 1. Similarly, let me write up the entries for every other row. What we see here is every row's sum now adds up to 1. This is equal to 1. Similarly, this row sum again is equal to 1, and the same holds for every other row, which implies AR1n is equal to 1n. Not only that, more importantly, AR is a non-negative matrix. So what do we have now? We have constructed a matrix out of the Laplacian matrix, or using the Laplacian matrix, which is now a row stochastic matrix. Note that as long as the epsilon chosen here is any value less than 1 by L max, the properties still hold. Let's write it. AR is a non-negative Rho stochastic matrix for every value of epsilon less than 1 by L max. What does this imply? It implies that we can construct infinitely many Rho stochastic matrices using a given Laplacian matrix. Some other property gets preserved in this form of construction. What is that? In order to see that, let me write both the Laplacian and the matrix AR side by side so we can compare them. So what we have shown here is the same diagram that we use for the example, and this is a Laplacian for it, and we chose epsilon equals 1 by 5 and constructed our Rho stochastic matrix. What do we observe in both the cases? The zero and non-zero patterns remain the meaning wherever the Laplacian has a zero entry, sorry, we have made an error here. Please note that in minus epsilon 1n must have 1 equal to here and 1 equal to here, right? Because the diagonal entries come now in the identity. Similarly, let's write it here. This is equal to 1 and this also must be equal to 1. Okay. Now let's come back to the zero non-zero pattern. For every off-diagonal entry, the zero and non-zero pattern remains preserved. And they correspond to this. And the same holds for every other row. The only difference being that we now have some added self loops in this graph, meaning now if I am to construct the corresponding digraph, what will that look like? It takes the following form. The difference now is that the interagent edges now remain the same. There's no change in that, but we now have a few self loops at one at node number 4 and the other at node number 5. Meaning, if G were a connected digraph here, if G was connected, then GAR is also connected. If she is disconnected, then correspondingly GAR is also disconnected. Meaning, if there are certain properties that we can derive for the non-negative adjacency matrix, the same structural properties will be retained for our original graph G. So what are the things that we can conclude? We already know from the theory on distributed averaging, which we read before, where we saw that if we have a formulation in this manner, where we have an adjacency matrix, which is Rho stochastic, and 1 seems to be a semi-simple eigenvalue. For example, here, if we solve, we know that 1 is a semi-simple eigenvalue. Equivalently, if we now construct the condensation graph for this network, here we see that there are a few strongly connected components. For example, 2 and 3 form a strongly connected component. And in fact, 1, 2, and 3 form a strongly connected component. and can be condensed to just one node. So let's write it. The corresponding condensation graph is this. We will have two more nodes, one for node number 4 and the other for node number 5. And this exactly will be the set of edges. This is some node 1 prime, this is 2 prime and 3 prime, where 2 prime is constructed out of node 4, 3 prime out of node 5, and 1 prime is constructed out of the nodes 1, 2, and 3, which form a strongly connected component. We know that the condensation graph now has two sinks. Hence, one is a semi-simple eigenvalue, which is repeated twice. If now 1 is a semi-simple eigenvalue, let us go back to our adjacency matrix, which is rho stochastic, and write up the expression. Suppose 1n is a, that is semi-simple for the particular example eigenvalue. So 1 is the eigenvector corresponding to the eigenvalue 1. Then obviously what I have is AR1n is equal to 1 times 1n. Hence, in minus epsilon L1n times 1n is equal to 1 into 1n. Let's quickly solve it. So it's this minus epsilon 1n is equal to 1n. Similarly, I times 1n is also 1n, so they get cancelled out. So what we are left with is epsilon this is equal to 0, 1n, meaning the eigenvalue 1 shown here corresponds to the eigenvalue 0 of the Laplacian matrix, meaning every eigenvalue 1 corresponds to the eigenvalue, this is eigenvalue 1 of AR corresponds to the eigenvalue 0 of the Laplacian, implies semi-simplicity of 1 leads to that of 0. So 0 of L we can write here, and similarly 1 of AR. So what do we see? That whenever 1 occurs as some simple eigenvalue of AR, which we know that if the condensation graph has two sinks, we know that AR will have 1 as a some simple eigenvalue. Correspondingly, we will also have the Laplacian having 0 as a semi-simple eigenvalue, which leads to the theorem stated as follows. Let's write now the main result. The main result goes this way. Let L be the Laplacian matrix of a digraph G containing n number of nodes. N number of nodes. Then let ns be the number of sinks in the condensation graph of G. The condensation graph is denoted as C of G. Then what can we always say? First is the eigenvalue 0 is semi-simple and it's repeated ns number of times. Or we can conclude one more interesting thing out of this. This result further implies that if G has a globally reachable node, then L has 0 as a simple eigenvalue. Why can we say that? Because now the condensation graph will have one sink. This is because CG has only one sink in this case. In this case, hence 0 occurs ns equals 1 number of times. This actually leads to a very interesting question. So what did we see here? We saw that ns is in fact repeated. The number of sinks in the condensation graph in fact gives us the number of times 0 occurs as an eigenvalue. Interestingly, there are cases when we have just one globally reachable node, in which case we know that 0 occurs only once. So now let me draw two different diagrams. First diagram looks like this. Say this is, in this case, suppose this is. Here, let me index the nodes in this manner. What do we observe? We observe that 3, we observe that G has a globally reachable node. Which is equal to node number 3. Implies 0 is a simple eigenvalue. Let us look at yet another digraph. Let me take this same digraph and modify this slightly. All that I've done is modified the edge direction, modified the direction of just one of the edges. Now what do we see? We see here that, let's call this G and this as G prime. G prime is strongly connected of LG, let's write. So here we are talking about 0 being a simple eigenvalue of the Laplacian. So now for G prime, We know that G prime, we can clearly see it's a strongly connected digraph. Is strongly connected. Is 0 an eigenvalue? Okay. The answer is yes. Every Laplacian has an eigenvalue 0. Number of sinks in C of G prime is clearly equal to 0. If you draw the condensation graph here, it will just condense to one node because it's a strongly connected component. Meaning the condensation graph does not have any sinks. However, yet 0 is an eigenvalue. And since there are no sinks, 0 we can say is a simple eigenvalue. This is a very important example. Why? It shows us that the simplicity of 0 being an eigenvalue cannot actually distinguish between the digraph being connected or strongly connected, meaning 0 can be a simple eigenvalue, and in some of the cases, the digraph, as we see here, can be an acyclic digraph. However, in some other cases, the digraph could in fact be strongly connected. We could show the same example for the case of an undirected network as well. Meaning, what exactly happens in this case? How can we actually distinguish using the spectral properties of the network between, let me phrase that again. If you want to distinguish a connected graph from a disconnected graph, or a strongly connected graph from a weakly connected one, can we use the spectral properties? In particular, can we use the 0 eigenvalue in any way to distinguish this? Now, we already know the answer to that is no. So, is there any other eigenvalue which can help us distinguish between a connected and a disconnected graph? This is something we will look at in the next lecture. So, I'll pause the lecture right here. In the second part of the same lecture, we'll try to first comment about the rest of the eigenvalues that we can get for a Laplacian matrix. Thank you.